Beginning with this lesson and going on for the next few lessons, we're going to take what we learned about science and nature in general and modern physics in particular to look at the lives of stars. So we're going to begin with the birth of stars today. Quick little review. What we're doing is we're taking pieces that we've learned about nature as a whole, and we're going to put them together to tell the story of how stars are born. So piece number one that we're going to use is energy. And what you need to remember about this is that pure energy can be thought of as waves of electrical and magnetic fields that spread out through empty space at 300,000 kilometers per second. This is what we think of as light or electromagnetic radiation. And we saw that electromagnetic radiation comes in different forms, from long wavelength, low energy radio waves to high energy, short wavelength gamma rays. And we saw that there is an inverse relationship between the wavelength and the energy, and therefore the temperature of an object giving off the electromagnetic radiation. So long wavelength means low energy and low temperature. Short wavelength means high energy, high temperature. Astronomers we saw use this to establish spectral classes for different kinds of stars based on their surface temperatures. We had the spectral classes O, B, A, F, G, K, and M in decreasing temperature. And we saw that these stars come in different colors and they peak in different kinds of electromagnetic radiation. And then very briefly, when we were talking about the distance ladder and finding distances in space, and we talked about one method called main sequence fitting, we looked at the Hertzsprung-Russell or HR diagram that relates spectral classes to and temperature, which are really the same thing, to how energetic the star really is, either luminosity or absolute magnitude. And we said that most stars, over 90% of all stars, fit on a region of the HR diagram called the main sequence, where there's a direct relationship between temperature and luminosity. The second piece we're going to bring in is matter. And we started off by saying that matter can be thought of as particles. The smallest particles are most fundamental. We didn't really say too much about this. It was mentioned in your article on the fundamental forces. But the smallest particles that scientists have discovered up to this point come in two classes. One of them are called leptons. Leptons include electrons and even tinier particles that we call neutrinos. The other type of fundamental basic particle that can't be broken down into anything smaller is the quark. And there are a bunch of different types of quarks, 6 types of quarks: up, down, top, bottom, strange, and charm, interesting names. But the important thing that we need to know about quarks is that you put quarks together to make up the more familiar particles to us, the protons and the neutrons. And the difference between them is that if you want to make a proton, you take 2 up quarks and you combine it with a down quark. If you want to make neutrons, you take 1 up quark and you combine it with 2 down quarks. So both of them are made of 3 quarks. But protons are 2 up and 1 down, and neutrons are 1 up and 2 down. Protons, neutrons, and electrons then, as you know, combine to make atoms with the protons and neutrons in the nucleus. So we can actually call these 2 particles together nucleons because they make up the nucleus, and the electrons zipping around in the energy levels. Atoms, you know, then bond to each other to make up molecules, and that's what builds up all of nature around us. But we learned from quantum theory that matter can also, and in fact needs to be thought of also as waves. That's the idea of wave-particle duality. And the important concept for us that comes out of this is that idea of quantum tunneling, the idea that particles, that subatomic particles can actually go places, do things, appear in places that they shouldn't be able to if they're only particles, because they can also move as waves. The third piece that we're going to bring in is the idea of forces. And you read an article about fundamental forces. There are 4 fundamental forces. The first one that Isaac Newton came up with and discovered is gravity, or Fg. It's the weakest by far of all the forces. But it acts on all matter, whether it's charged, whether it's uncharged, whether it's a lepton, whether it's a quark, it acts on all matter. And it's also weird in that it's the only one of the forces that's always attractive. It always, always, always pulls matter together. And we're going to see that this is really important for understanding the birth of stars, for understanding black holes, and even speculating about the fate of the universe. The second force, fundamental force, that acts on the scales we're familiar with is the electromagnetic force, or just electromagnetism. Electromagnetism also acts at all distances. It gets weaker and weaker and weaker the further away 2 particles are, but it's always there. But it only acts on charged particles. Unlike gravity, which acts on all particles, the electromagnetic force only affects charged particles. So the electromagnetic force, for example, would act on protons, but it wouldn't affect neutrons. Neutrons live in a universe that is one which doesn't actually have an electromagnetic force, or it doesn't feel the electromagnetic force. Electromagnetism can attract if the charges are opposite, but unlike gravity, it can also repel if they're like charges. And this is why, even though electromagnetism acts across all distances and is much, much stronger than gravity, on the largest scales of the universe, it actually cancels out all the attractions between opposite charges. The repulsions between like charges will cancel out. So we don't, for example, experience much electromagnetic force coming from the sun, while we do experience a lot of gravitational force coming from the sun. The third and fourth fundamental forces are unfamiliar to us because they are very, very short distance and they act only within the nucleus. And so we call these the nuclear forces. We have the strong nuclear force, which is, not surprisingly from the name, the strongest of all the forces. It's millions and millions and millions of times stronger than gravity and about 100 times stronger than electromagnetism. It acts only on particles that are made of quarks. Okay? That fundamental type of particle that we mentioned just a little while ago, that would include protons and neutrons, but not electrons, because electrons are leptons. So protons feel gravity, protons feel the electromagnetic force, and protons also feel the strong nuclear force. Neutrons experience gravity. They also experience the strong nuclear force, but as we mentioned, they don't experience electromagnetism. It has no effect on them. What does the strong nuclear force do? Well, because it acts on quarks, it does 2 things. First of all, it holds quarks together to make protons and neutrons. So if the strong force holds 2 up quarks and 1 down quark together, we get a proton. If it holds 2 down quarks and 1 up quark together, we get a neutron. And then it also holds the protons and neutrons together to make the atomic nuclei. And that's important because remember, the nucleus contains protons, lots of protons. If you have a uranium element number 92, there are 92 protons crammed together in that nucleus. They're all positively charged. They're all going to repel each other with the electromagnetic force because like charges repel. Well, what overcomes that repulsion and keeps the nucleus from flying apart? It's the nuclear strong force. So if the nuclear strong force is so strong, why don't we experience it in our everyday lives? Because it only acts over very, very, very short distances, distances of a few femtometers. A femtometer is 10 to the negative 15 meters. So 0.00000000000000001 meter. Okay, that would be a quadrillionth of a meter or 1,000 billionths of a meter. And the strong force is both attractive and repulsive. Interestingly, it's attractive at a distance of only a few femtometers, about the size of the nucleus of an atom. But if you try moving quarks closer than a few femtometers, if you try to move them within, say, 1 femtometer of each other, then the strong force actually changes from being strongly attractive to being strongly repulsive. In other words, it pulls quarks together very, very strongly at short distances, but if they get too close to each other, then it strongly repels them. The fourth force is the weak nuclear force. And we're not going to say too much about it other than that it actually acts within quarks, it affects the nature of quarks, and it can turn quarks from one type into another. So it can, for example, turn an up quark into a down quark and vice versa. And the nuclear weak force is important in some forms of radioactivity like beta radiation and will actually meet an important role for the nuclear weak force. So in the next video, we'll put some of these pieces together into bigger pieces.